Welcome in subject mechanical system design. Today we will see the problems on unit number 6, that is optimum design. So the problem number 1 we will discuss first. So the statement of problem number 1 is as follows. Design a tensile bar of length L is equal to 200 mm to carry a load of 5 kilonewton for minimum cost out of the following material. Use factor of safety equal to 2. So the materials are given steel, aluminum alloy, titanium alloy, magnesium alloy with the density, then material cost and yield strength in megapascal. So this is the problem statement. Now our aim is to design to find out the cross-sectional area of the bar to minimize the cost, that is nothing but optimization of the cost. So the length of the bar is given. So the tensile bar of length 200 mm is given. Then 5 kilonewton is the tensile load applied at the end of the bar. Then our prime objective is to find out the cross-sectional area to minimize the cost. So we have to optimize the cross-sectional area of the material. Then a factor of safety is given as a 2. Then in a table you can see the various materials are given, and for following material we have to design the tensile bar with the optimum cost. So to find out the area to minimize the cost CM, the primary design equation developed is given as below. So PDE in the form of minimizing the cost CM is equal to C into volume into density. So CM is equal to C into bracket volume is rho into A into L into G, that is the product of volume into density. So this equation is called as a main design equation, that is also called as a primary design equation. So here in this diagram you can observe a tensile bar with the round cross sectional area, circular cross sectional area. A is the cross sectional area of the material. Then axial load or tensile load is applied at bar ends. Then L is the length of the bar. So our aim is to what is the effect on the stress. Then second is the subsidiary design equation. So the tensile stress induced in the bar is given as a sigma is equal to P upon A, where P is the load applied and A is the cross sectional area of the material. So this is the second equation, subsidiary design equation. Then third one is the limit equation, that is nothing but a sigma is less than or equal to SYT upon factor of safety. So this will use the limiting value for the stress. So these are the three equations that we are going to see, or we have to find out the values for that three equations, that is the CM, primary design equation, main design equation it is also called. Second one is a stress induced in the bar, and third one is a limit value for the stress based on the ultimate tensile strength and factor of safety. Now we have to, in next step we have to develop the new primary design equation when we combine the subsidiary design equation with the primary design equation. So here we are having a primary design equation, CM is equal to C into rho ALG, and subsidiary design equation sigma is equal to P upon A. So from here we are getting the area is equal to P upon sigma. So whenever we are combining these two equations, area will going to cancel here. And what is remaining in the new developed primary design equation? Cm is equal to C into rho into P upon sigma L into G. So here G is the acceleration due to gravity, L is the length of the bar, P is the load, axial load or tensile load, sigma is the stress, rho is the density, and C is the cost, where Cm is the minimizing cost. Next, what we get the developed primary design equation. Now in next step, we are combining the limit equation with the primary design equation. So here our new developed primary equation is this: C in Cm is equal to C into rho into P by sigma into L into G, and limit equation is given as a sigma is less than or equal to SYT upon factor of safety. So here we will get the final equation for the minimizing the cost: C into rho into bracket factor of safety into P. Means simply here we are putting the value of sigma in. From limit equation we are getting the sigma value, and we are putting that sigma value into this primary design equation, so that we will get the new final primary design equation, that is a Cm is equal to C into rho into factor of safety into P divided by SYT into L into G. So from this equation, once we put all the values for a particular material, what we get the which material is the best suitable for minimizing the cost, that we will get. So the limit equation effect can be directly induced in or included in developed primary design equation in normal case. So the developed primary design equation, final design equation is the Cm is equal to C into rho into factor of safety into P divided by SYT into L into G. So this is final developed PDE for minimizing the cost. Then we are separating the material parameters MSF. So Cm is equal to Cp by rho divided by SYT into GPL into factor of safety. So final design equation will be Cm is equal to material separation parameter or factor MSF into GPL into factor of safety. Therefore, a material parameter will be calculated by using the formula C into delta divided by SYT. So now we will see for our actual values. So here for steel material, delta is given as a 7,500, C is 16, and yield strength is a 130. Then MSF is calculated for the steel, which will be 923.077. Therefore, for aluminum alloy, it will be comes as a 1919. Then for titanium alloy, it will be 25,600. For magnesium alloy, it will be 3,360. So the sigma is equal to P upon A is our standard formula. Therefore, stress is equal to SYT upon factor of safety. So that will be the 60. Then A is equal to P upon sigma. So the cross sectional area will be 76.923 mm square. So in this way, we can select the, or we can calculate the cross sectional area for minimizing the cost, and we are selecting the best suitable material for which MSF value is less. So these are the parameters with the material which can be best possible optimum design for the tensile bar.